So, yesterday we were describing some of the semiconductor based photo detectors or sensors. So, their approximate wavelength ranges. So, depending upon, let us say generally we use silicone photo detectors, you can see that the wavelength ranges between 400 and 1100 nanometer. Okay. And with some modification, the wavelength range can reduce to even 180 nanometer or so, in terms of improving its texture, surface, etc. So that absorption becomes right significant enough to produce electrons accordingly. Okay. Electrons in hole pairs accordingly. Okay. And its bandwidth is it's also given, and if we are talking if we want to improve its efficiency, etc. These are all pin photodiodes, and if you want to improve further its efficiency, etc., we use avalanche type photodiodes. So, which has a structure corresponding to, so there is a P region, intrinsic region, N region, and in this between P there is a multiplication region. So, and it is a very thin film, okay, so that the electrical field acting on it will be very large to provide multiplication. It is known as multiplication region. So, the electron which are generated will undergo multiplication factor in the range 100 to 400. That means accordingly the current from the photo detector will increase accordingly. Okay. So, that is the factor. So, generally the responsivity, okay, of any of the photo detector is given by the parameter. Okay. It's given in terms of ampere per watt. Okay. However, it is nothing but quantum efficiency eta into charge. Electron charge is nothing but 1.6 into 10 raised to minus 19 coulomb into and h into nu, okay, where photon energy corresponds to. And for photo avalanche detectors, due to the multiplication factor m, the responsivity improves by the factor m. Okay. Now, if you see what is eta, eta is nothing but quantum efficiency. Okay. So, what we considered responsivity of a detector as eta into charge divided by h nu. Okay. So, here eta is quantum efficiency. Okay, which is a number of electron and hole pairs generated, okay, divided by number of photons, incident photon, number of incident photons. Okay. So, this is R is, as I told you, is nothing but responsivity. Okay. So, and Q is is in our case when electron charge is nothing but 1.6 into 10 raised to minus 19 coulomb. Okay. So, we can depending upon material characteristics based on the number of incident photons, number of electron hole pairs will be generated, and indirectly material characteristics determines quantum efficiency. larger the quantum efficiency, of course, the responsivity, which is measured in terms of current which is generated based on the input, right, power W. Okay. So, that is the factor which is responsible. And now, eta, this R is responsivity of a detector, and the photon, the current, okay, which is generated, the primary photocurrent which is generated, primary photocurrent which is generated due to, right, interaction of photons, incident photons with the detector surface. Okay. Primary photocurrent, semiconductor material may be in this case, primary photocurrent which is generated from this is given by IP, which is given by responsivity into P input, right, the power, whatever may be, right, photo of, right, optical power or whatever, okay, which is optical power. R is nothing but the responsivity, okay, will give you primary current which is generated. So, these factors are important. So, if the responsivity, right, which depends upon quantum efficiency also is high, then automatically the photo current which is generated will be of right, significant value, and based on that even another aspect which comes into picture, which is signal, which is, right, which is achieved. So, maybe one example, I just want to give you some examples that can give you okay. So, maybe but this is okay, maybe let us say of course, it is obvious, but just to get an idea in terms of number values. Okay, I am trying to give one example. Let us say an indium gallium arsenide photo detector, pin photodiode is there. Okay, we are considering a pin photodiode which is indium gallium arsenide. So, indium gallium arsenide pin photodiode works in the wavelength range 1300, 1200 or 1000, right. Maybe we will just see, right, indium 1100, 1300 means basically 1100 to 1700 nanometer range. Okay. So, we are considering indium gallium arsenide pin photodiode and its wavelength to which it is working, let us say 1300 nanometer. Okay. We would like to use, okay, and the assume incident power, okay, of light on this photo detector, let us say P in is 300 nanowatt. So, 300 into 10 raised to minus 9 watt, okay, is the power. The temperature, working temperature is 293 Kelvin. So, it is a room temperature, and the, so we right, we would like to estimate basically, and what is the, okay, quantum efficiency. Let us say quantum efficiency is at this, right, wavelength eta is, it is given as, let us say it is around 0.9 or so. Okay. So, what will be the photo current which will be generated from here. Okay. So, we know photo current is eta. So, basically responsivity, or maybe photocurrent is nothing but the responsivity into P input. Now, responsivity is nothing but N Q upon H nu. Nu is C by lambda. So, into lambda to P in. Okay. We know eta 0.9 we know Q, which is 1.6 10 raised to minus 19 coulomb, lambda is the wavelength 1300 nanometer. So, right, accordingly we can right, convert it into meter. Then h is the Planck's constant, c is the speed of light, p in is also given. So, if we substitute all these parameters which are available, okay, right, q is 1.6 10 raised to minus 19 coulomb, c is speed of light 10 meter per second, h is Planck's constant 6.626 into 10 raised to minus 34 joule second, and all these parameters are given. So, from this IP will be approximately 0.28 microampere. Okay, this will be the outcome. Okay, and in order to right obtain right measurable, right, means which measurable output, we may use amplifier right associated with it. And if we are using let us say photo this avalanche photodiode, avalanche type photodiodes, then what will happen, magnification factor will come into picture. So, the value m will be 100 to 400. Okay, let us see what is the value here. Let us see if you are using avalanche photodiode indium gallium arsenide, the gain factor m, right, is around 20 to 250, maybe around 100. So, automatically the output power will appropriately improve, it will become 2.8 right milliampere. Okay, output, not power but the current, okay, photo current will accordingly enhance. Now, there is one more factor associated with this type of detectors is maybe I will put it in terms of signal to noise ratio. Okay, which is also known as SNR. Okay. So, this signal to noise ratio can be estimated depending upon the type of detectors etc. But what are the parameters that we estimate generally in case of estimating the signal to noise ratio, which is basically SNR is given by signal power from photocurrent, okay, to the total sum of photodetector noise power plus amplifier, right, if we are using amplifier noise power. Okay. And it is also given by mean square signal current, okay, divided by summation of mean square noise currents. Okay. Now, this noise currents are due to short noise which is random in nature. Okay. So, in case of photodetector, sometimes electron hole pair may be generated due to the energy band gap may be small, etc. This randomly it may get generated irrespective whether power, whether the light is photon is falling or not. So, that randomness of a photodetector it's operating in though, even though there may not be photon level, there may be some short noise which is given by which is one factor. The other factor is thermal noise. Okay. thermal noise. Depending upon the temperature, right, operating temperature, surrounding ambient temperature, sometimes the electron hole pair may be generated, and those electron hole pairs which are generated are noise with respect to the power what we would like to measure, optical power. And the third one is basically dark current, okay, dark current, which is generated. Okay. So, there will be some ambient right light which may photons which may interact with the detector and produces dark current. Okay. So, which produces the current which is known as dark current, because that is not the current what we are trying to measure. So, this short noise, thermal noise, dark current are the three factors, they add up to the total this noise current. Okay. And so, when you see the photo detector output on with the oscilloscope etc., you will see that there will be some small spikes. Of course, the amplitude may be very small, but those spikes will be there. So, if we use statistical approach to estimate this mean square noise current, so that noise current becomes right a very it will become significant when signal to noise ratio is very small. That means, when the signal what we are trying to measure is very small, of the order of nanoampere, means very small nanoampere, few tens of nanoampere etc., then the noise current which is also of the similar level becomes significant. Okay. And that is why this signal to noise ratio estimation is important. I will be giving you standard methods to estimate such there are standard formulations to estimate this values. So, I am not describing those standard equations which are given by most of the what shall I say, even the detector means sensor manufacturers. So, those signals adds up to provide basically the signal to noise ratio. Okay. And we can estimate indirectly noise equivalent power, correct. If we know the signal to noise ratio, then for SNR equal to 1, whatever is the signal power which is known as noise equivalent power, okay, which can also be estimated. So, for example, just as an example, if I give, if we have let us say signal to noise ratio, okay, which is R square P in square, correct. We know I P is equal to R into P in, correct. Right. So, divided by, and let us assume that dark current as well as short noise is very negligible as compared to the thermal noise. So, the thermal noise may be an right important factor, let us assume, okay, just to give you an approximate. So, R square P in square, and thermal noise in terms of mean square thermal noise is given by 4 kb T, that is temperature, Be, which is a bandwidth, divided by some resistance, right, characteristics of the semiconductor. Okay. These formulations are available in the right most of the this sensor catalogs etc. Now, this signal to noise ratio when it becomes 1, okay, this SNR when it becomes 1, the corresponding P in, okay, corresponding P in is known it is termed as noise equivalent power, okay, NEP, noise equivalent power. So, sometimes right equivalent power which is equal to 4 square root of 4 kBT B E upon R L, right, divided by response characteristics R. Okay, it is given by this. So, this noise equivalent power will decide, right, our signal to noise ratio parameter, which is 1. So, most of the catalogs will give you what is the noise equivalent power. Okay. So, from there we can estimate what should be the input power that a sensor can measure. We are neglecting, okay, we are only here I am just shown you with thermal noise. It will there will be short noise, there will be dark current noise, etc., which will add up. So, total noise will be known, and from there also we can estimate. Okay. So, this is the way that we can estimate the sensor this aspects. Now, if we arrange all this sensor in an array, okay, so array, we can achieve the different okay, this okay, these are all formulations, of course it will be label. So, this, so if we arrange, maybe I will show you picture, if we arrange this sensors in an okay, so let us say there is a transparent gate. Okay. So, incoming photons are coming through and then they transfer. Now, this is one cell, okay, one cell. Okay. For one stage of a charge coupled device. Okay. So, here incoming photons they come and then they generate corresponding photocurrent, correct. When they interact with the sensor material, let us say silicon, right, detector, it will generate photocurrent, but it is equivalent to generating photon induced charges, right. So, number of such electron pairs generated into Q will be that, right, or that many charges which are generated. Now, this charge in case of if we arrange these detectors, okay, each sensor detector is arranged in a row. So, row 1 has 1, 2, 3, 4, right, such detectors, row 2 has 1, 2, 3, 4 detectors. So, like that there are 4 by 4 detectors, correct. So, 4 by 4 detectors arranged in an array, and each of them accumulates this photon induced charges, and these charges are then transferred through electronic means, transferred to the transfer register to transfer register, right, are transferred to the transfer register to measure the output. Okay. So, row wise output, each register wise output, or column wise output, everything can be generated using this CCD array. Okay. So, charge coupled device is nothing but an array of all these photo detectors, and the electronic approach, circuit approach, allows them to capture the information in a spatial, right, way, spatial information. Okay. So, two dimensional information can be achieved with the help of array detector arrays arranged in this fashion. Now, charge coupled device has the advantage that the full the complete area of the detector is available to detect this, right, charges, etc. The right, and if we can couple this charge coupled device can be even right, can be with a better and better amplification factor, right, such as avalanche type, right, detectors, etc., can become even much more sensitive device in order to detect the let us say detect the photon means or optical power in a two dimensional right way, or capture the image information etcetera very easily, and that is the basis of CCD camera, right. So, that is being used. However, there is another approach, okay, similar to the charge couple device, but instead of charge being stored etcetera, each of this semiconductor sensor, okay, consist of various such switching components coupled with each photodiode. Okay. So, each sensor photodiode will have corresponding 4 switching right components, okay, for reading, for resetting, setting as well as for output, along with the junction capacitor to provide the output over here, and each of them captures the information, and the processing becomes much faster. Instead of transferring the charge from one place to another place and then analyzing the components in charge couple device in CCD. So, what has happened because of the semiconductor technology which evolved over the time in last 10 to 15 years, you must have seen that previously the cameras were charge coupled CCD device, now they are all CMOS device. So, basically each sensor has such circuitry, okay, which has all the 4 such switching components combined with the circuitry. So, it is much faster in terms of response characteristics. However, the efficiency in terms of photo current generated, okay, is slightly lesser, because the some part of its area is being covered by such other devices and not for right. So, the efficiency wise CMOS devices may be slightly less efficient as compared to charge coupled device, but they are also useful. So, basically all these devices are made up of same either silicon based detectors or indium gallium arsenide based detectors etcetera, but they are either based on CCD approach or CMOS approach. Okay. So, as an end user we may be using such devices, but the configurations are such. Now, there is one more device which is also very important, which is which works in the mostly in the visible and range or UV range to near infrared range at the most, which is known as photo multiplier tube, okay, a PMT it is known as. Now, this device is slightly different from the semiconductor based device what we discussed. Here the incoming photon interacts with photo emissive cathode, okay, or basically this cathode generates electrons based on the number of incident photons. Okay. Of course, it has a quantum efficiency associated with it, right. Number of electrons generated divided by number of incident photons will give the quantum efficiency. Okay. Now, corresponding to its quantum efficiency based on the number of electrons generated, those electrons in turn undergoes multiplication, okay, rather amplification etcetera. So, using external other arrangements. So, they are the amplifiers are over here are nothing but they are known as diodes. Okay. So, each of these diodes are under certain potential, potential is applied, so that the primary photo electron will get accordingly accelerated, will generate more electrons from this after impinging on this dinodes, okay, will generate more electrons. So, it undergoes multiplication, right, through passing through multiple such dinodes, it will generate multiplication, means number of more and more number of electrons, and finally the anode is used and the output is captured, okay, measured based on the number of electrons which are generated, okay. And this photomultiplier tube will be in a high vacuum condition, it is around 10⁻⁻⁴ Pascal inside, okay. So, there are different configurations of this photomultiplier tube, it can be side, right, or it can be light can be directly impinging on a photomultiplier tube directly, and then photoemissive cathode will generate electrons from there. So, this is from where electrons are generated and then multiplied while getting transmitted, okay. So, this approach of photomultiplier tube is also useful in order to generate output with a very high right, means signal to noise ratio is quite, means it can or rather I should say that with a very low input power, okay, nanowatt order or even small optical power, you can still see the very large signal strength, okay. Now, the windows which are used over here, okay, the optical windows which are used over here, this optical windows etc., are basically made up of the material which allows even UV light transmission, okay, not only the visible and near infrared, UV light transmission. So, generally MgF2 magnesium fluoride material is used. If you are using borosilicate glass, right, which is in a trade name, in a outside in a with a trade name, it is known as BK7, okay, glass. If it is borosilicate window, it will go up to 300 nanometer or even means at shorter wavelength light, optical light will get absorbed, right, by this borosilicate glass. So, it can work only from 300 nanometer or above, okay, as a window. If you are using silica glass, it may work up to 170 160 nanometer, okay, at the most silica glass. But if you are going with MgF2 magnesium difluoride, it can work with even a shorter wavelength range this, okay. So, windows are selected based on which wavelength range we are working on, as well as the photocathode materials, okay, they are bialkali materials, either Sb, Rb, rubidium, cesium, antimony, rubidium, cesium combination or antimony, potassium, cesium combinations etc. Okay. So, they are bialkali materials and their quantum cathode radiance sensitivity, okay, ampere per, very similar to the responsivity, right, is milliampere per watt. Or quantum efficiency is given by this, okay. So, sensitivity is given by this solid line, and quantum efficiency has been shown by dotted line over here. You can see that the this photomultiplier tubes, they have very good this efficiency, quantum efficiency in the visible range, okay, 400 to 700 800 nanometer or so, okay. So, this photomultiplier tubes are very useful for low means visible range, right, measurements etc. and right. So, this is basically a photomultiplier tube materials, okay, and that they are very much, their efficiency is quite high, and as I told you, since the sensitivity is right quite large, it allows very small input power as the measurement, okay. So, and basically you can say, with respect to the supply voltage. So, I basically even the is it is the multiplication factor, okay, of the PMT photomultiplier tube depends upon number of such secondary emissions, okay, which are taking place, and it depends upon a number of such stages which are used, and in turn it depends upon the voltage what is applied to the photomultiplier tube. So, if we are using 9 to 12 dynode stages, and depending upon the photomultiplier tube voltage what we apply, we will see that the sensitivity right enhances further. So, if I am using input power to the dynode, input voltage to the dynode as around 500 volt, the efficiency sensitivity may be x, gain will be of the order of particular value x, but then if I apply large voltage of around 1 kilovolt, the gain will multiply by so many times. Okay. So, that is what is shown over here. So, generally for photomultiplier tube we apply the voltage, okay, external voltage between 750 and 1000 volts, it is a right 1 kilovolt right voltage applied. So, this system is little complex in terms of external power supply requirement etcetera, as compared to the photo detectors what we semiconductor based photo detectors which are very small, compact etcetera, and here it will be a large size with a power supply to supply the voltage of the order of 1 kilovolt or so, but as compared to the photo detectors the efficiency is quite large. You can see that it can right, it can give you output 100 times more in terms of responsivity, ampere per watt is quite large, okay, right. So, that is the case. Secondly, another factor which comes into picture, because as you apply larger and larger voltage the dark current increases. Even in a dark room it will be able to capture some photons, okay, of this light which are maybe getting transferred in the dark room somewhere, generated such photons also it will be able to capture. Okay. So, we will have to whenever we are using such photomultiplier tube sensors, we cannot expose it to the sunlight etcetera, it will get damaged even to the tube light, because the radiant output will be so large based on the number of photons which are generated. So, they are used in a dark environment because the sensitivity is also much higher. Okay. So, of course, this we need not, but with temperature the dark current also increases, but at room temperature it works very well. So, right. So, that is basically this is of course description about photo multiplier tube. So, if we consider in terms of photo detectors, generally use photo detectors for our right biophotonics application, either most of the time we will be using right semiconductor based detectors, okay, and reverse bias with amplifier right semiconductor based detectors, and for visible range it will be silicon, and for near infrared range it is indium gallium arsenide, okay, detectors. And then there are certain photo detectors which if we want to work, so this is let us say 1.1 to 1.7 micrometer wavelength range, this is 400, so 0.4 to 1.1 micrometer range wavelength range, right, lambda. And if we want to work beyond this, then we will have to use indium antimony semiconductor based photo detectors, or lead based photo detectors are available. Okay. These indium antimony based photo detectors etcetera, they work from 2.5 or 3 micrometer to right 5 or 6 or right 5 micrometer or even longer wavelength range. Okay. HD CT. There are different types of such materials they work, but here you require cooling, okay, cooling of the photo detector. Why? Otherwise the dark current will be very large, the photo band gap is much smaller, wavelength is right, it is trying to measure longer wavelengths. This and array of photo detectors are also possible, either with CCD configuration or with CMOS configuration, okay, to provide right image, or we can use photocathode type, right, that is nothing but photocathode type. So, which is which can provide you with the help of diodes attached with it photomultiplier tube, okay, to measure the power, okay. And there is one more approach, a thermal right approach. Of course, the IR detector, thermal detectors what you see are nothing but CMOS device with let us say the IR sensors are either indium gallium arsenide or some ones etc. Okay. So, they detect the basically infrared emission, right, based on the body temperature, right, surface temperature, electromagnetic wave radiation is generated and that wavelength is captured. Of course, the wavelength is in the order of few micrometer, it may have very less sensitivity, but using some right materials combinations and amplifiers, they can measure right a very small that means long wavelength right measurements are possible, okay. And that is why they are very costly. This may be of the order of few hundred rupees or even less than that, silicon photo detector, okay, while indium gallium arsenide will be in terms of few thousands or right, and each one will be each detector. So, array will be of right few lakh rupees you can say, right, it is quite cost wise it is quite. So, 3000 rupees array detector, okay, half inch. So, 12 millimeter by 12 millimeter right square, silicon photo CMOS will be of the order of 3,000-4,000 rupees camera, right, CMOS. But if you use indium gallium arsenide, it will be of the order of few lakhs, okay, 7, 8, 10 lakhs, okay, depending upon, right, because the manufacturing the material these things it's quite complex, okay, right. So, this is what we know now. From next class we will start with biomedical, right, how different right techniques related to either from the photonics device point of view, biophotonics device point of view, how it can be made. Thank you very much.